Everyone, this is Mrs. Grazafi, and we're on 10.01 Algebra 2 today. So we're starting a new unit on probability, and this is going to be our last new unit, which is kind of exciting. And then after this, we'll do a little bit of more general review as well. So today I wanted to just do a little intro into probability. For some of you, hopefully it's a little bit of review, at least in the beginning, like tree diagrams, stuff like that. But just basic stuff that you should know when finding probability. So what is probability? It's the probability of an event occurring is given by a ratio. And to find that ratio, you take the number of times you want the event to happen or that it's going to occur, and you divide it by the total number of observed occurrences. So, if we are looking at if a coin is going to land on tails, then we know there is one tail on the coin out of two. So it would be a probability of 1/2 or 1 out of 2. So N of E represents the number of outcomes that fall into event E, and N of S is the total number that fall into the sample space. So it's just what you want out of your total. So the top is what you want, the bottom is the total number of occurrences. Now, probability is always going to be between 0 and 1. Be any decimal or fraction between 0 and 1. 0 means it's not going to happen. And 1 means it is happening. So you are talking in terms of 0 to 1, or you could also be talking it from 0 to 100%. So you're not going to go below 0, but you're not going to go above 100% probability, because if you're at 100% probability, it's definitely happening. So number 1 says a fair coin is flipped 3 times and the result is noted each time. The sample space consists of ordered triples, such as HHT, meaning a head on the first toss, a head on the second toss, and a tail on the third toss. Draw a tree diagram to show all of the different outcomes in the sample space. So this is called theoretical probability, first of all. Theoretical probability, because it means this is happening in theory. So in theory, you're going to get a head to occur 1 out of 2 times. Will that always be the case? No, because it's not perfect. But in theory, and if you do it a lot of times, so if you do it thousands of times, then it will start to look more and more like the theoretical probability. You're not doing any surveys, you're not doing any data collection. It's just in theory what would happen. So when we draw a tree diagram, I always kind of like to start at a point. And I think of when I draw the tree, I'm going to draw it going sideways here. And I think about what's my first question, or what's my first thing that's going to happen. And the first thing I'm going to do is I'm going to flip a coin. So when I flip the coin, I have 2 options. I'm going to either get head or I'm going to get a tail. That's the first flip. So let's say I got a head on the first flip. Now what could happen on the second flip? Well, for the second flip, I could again get heads or tails. Well, let's say I got a tail on the first flip. What could happen on the second flip? I could again get heads or tails. And then on the third flip, we now could say I got heads the first, heads the second. I could get heads on the third, or I could get tails. If I got heads on the first, tails on the second, I could get heads or tails on the third. And the same for these. So these red is your first flip, blue is your second flip, black is your third flip. So the question says, list all your outcomes as ordered triples, and how many of them are there? Well, before we list them as triples, we can figure out how many outcomes we have here. Because we have heads, 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 that's 1. Heads, heads, tails is 2. And then we have heads, tails, heads is 3. Heads, tails, tails is 4. Tails, heads, heads is 5, 6, 7, 8. So there are 8 possible outcomes. What are they going to look like? Well, here's where we can list them. So heads, heads, heads is your first one. The second one is heads, heads, tails. The third one is heads, tails, heads. The fourth one would be heads, tails, tails. The fifth one would be, now we're going down to the tails first. So tails, heads, heads. The sixth one is tails, heads, tails. The seventh is tails, tails, heads. And the eighth possibility is tails, tails, tails. 8 possible outcomes if we flip a coin 3 times. Now for part C, it says find the probability. So tree diagrams, that's not finding probability. When I say there's 8 possible outcomes, I'm not saying that the probability is 8. I'm just saying there's 8 different outcomes that we could have if we flip this coin 3 times. So if we want to find probability, we want to look at what we want. So for the first one, we want all heads. So we're looking through each of our outcomes here, and how many of them have all heads? Well, really, there's only one, right? That first one right here. So one outcome has all heads out of how many? Out of 8. So the probability of getting heads is 1 out of 8. So remember, it's how many you want out of your total. So in terms of our notation up there, it's the number of all heads. How many times do we get all heads out of our entire sample space? The next one says exactly 2 heads. So if you didn't write out all the sample outcomes, you could do this right from this top tree diagram as well, looking for how many of these outcomes have 2 heads in them. Exactly 2 heads, by the way, because the first one has 3 heads, so it has at least 2, but not exactly 2. And then your second outcome has 2. So down here, it's a little easier to see. This one has 2 heads. This one has 2 heads. The next one has 2 tails. This one has 2 heads. And it looks like that's it. So we have 3 out of 8. So our probability of getting exactly 2 heads would be 3 out of 8, or 3/8. And the last one here says the probability of getting all heads or all tails. So I've got, this one is all tails, this one is all heads. So the probability of getting one of those is 2 out of 8, which reduces to 1/4. Or as a percent, you could say there's a 25% chance the coin will land the same 3 times in a row. Will land the same 3 times in a row. So sometimes percentages are helpful to visualize it. Sometimes we like to do them as fractions, and usually the problem will specify, and if it doesn't, you can do either one. Okay, so now we're going to talk a little bit about sets. And I'm not sure that you guys have talked about sets much in the past. It used to be part of the algebra curriculum. But a set is just a collection of things that satisfy a well-defined criteria. Now, inside the set, we call them elements. And typically we talk about them using, and what we're going to talk about is using a die and a coin. You can do it with spinners. You can use anything. With probability, though, we tend to look at things such as those. So a subset is just a set whose elements are all contained within another set. So it's kind of like a set inside of a set, a subset. Number 2, consider an experiment where we first toss a coin and note the outcome, and then we roll a 6-sided die and note the outcome again. Part A says write the set of ordered pairs such as H4, meaning first I flipped the coin, I got heads, and then I rolled the die and I got a 4. By the way, die is singular, dice is plural. that represents all outcomes for this experiment in roster form. So just as a list, recall that this is called a sample space, and we're generally going to call this set S. So S means my first thing I could get is, let's say I get heads on the coin and a 1 on the die. And let's just go in order so we don't miss any. So let's do heads, and then I get a 2. I could get heads and a 3. I could get heads and a 4. Heads and a 5. And heads and a 6. Or I could get tails and a 1. Tails and a 2. Tails and a 3. Hopefully you're getting the idea here. Tails and a 4. Tails 5. Or tails 6. Okay, so we have 12 different possible outcomes in this sample space. Part B says, write a set of ordered pairs that represent the event of getting a tail and an even number. Call this set A. And then we want to know, is A a subset of S? And this is the notation for a subset. It's like a sideways U with a line underneath it. Kind of like an inequality symbol, less than or equal to, but it's not pointy, it's rounded. All right, so we want a tail and an even number, and we're going to call it A. So A could be a tail, and what's the first even number on a 6-sided die? Well, 1's not, but 2 is. We could get a tail, and the next even number would be a 4. Or we could get tails and the next even number, which is a 6. So to decide if this is a subset of the original, we want to look to see if all 3 of these are included in our original sample space. So I see a T2, a T4, and a T6. So we would say yes, that A is a subset of S because all the ordered pairs are in S. So a subset is either the same exact size. So technically, if I had listed for A all 12 of these from S, that's still considered a subset. So it's a subset of itself, even if it's exactly the same thing. Or it could be less than that. So that's why it's kind of like a less than or equal to symbol. It can be any combination of any of these 12 things, as long as they're all from S. And that would be a subset. Another vocab word that we'll talk about is a complement. So it says the complement of set A will be all the events in the sample space S that do not fall into set A. So a complement is just kind of like the opposite. So if this is set A, the complement is anything except those 3. And that will be the complement. We're going to call it B. But also know there's some other notations you could see for complement. So B is whatever's not in A. Sometimes we use a little apostrophe here, like an A prime, and that's called the complement of A. And sometimes we use a little C up here to represent complement. So in B, we would have H1. This one's going to be a much bigger one. H2, H3, H4, H5, and H6. And also we'd have T1, not T2, because that's right here. T3, not T4, and T5, but not T6. So this would be the complement. B is the complement of A. Together, they make up the entire set S. All right, now let's talk about probabilities of these. So up to this point, talking about sets, it's just listing things and seeing what's inside of the set. We're not actually finding probabilities. But now I want to find the probability of getting one of these 3 things in set A. So to do that, I take how many outcomes do I have in set A? Well, I have 3 outcomes in set A. How many total outcomes do I have in set S? So there's 3 outcomes here, and there's 12 outcomes here. So it's 3 out of 12. Or if you wanted to reduce it, you would get 1/4. Or you could write it as a decimal, 0.25, or as a percentage, 25%. Remember, to change a decimal to a percent, you move your decimal 2 times to the right. Now let's find the probability of B. So how many elements do we have in B? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 out of how many elements in set S? There's 12. Again, you can reduce that to get 3/4, or you could write it as 0.75 or 75%. If you were to add these together, 25 and 75, you get 100. 0.75 plus 0.25, you get 1. 1/4 plus 3/4, you get 1. So you either get 1 or 100%. So what that means is you're either going to get the probability of getting A or B is 100% because A is including everything that's not in B, and B includes everything that's not in A. Together, they make up all of set S. So that's why if you added them together, then you would get 100% of set S. Okay, so that's some probability using sets. And the next thing we're going to talk about is we're going to look at some Venn diagrams as well. And then we're going to continue talking about our sets as well. So consider the spinner shown below that has been divided into 8 equally sized sectors of a circle. So it's equally likely that you land on any of these 8 spots. The spinner is spun once. In this experiment, we will let A be the event of it landing on an even number, and B is the event that it lands on a prime number. Remember, prime numbers only multiply, the only factors would be 1 in itself, but also remember a little tricky here that 1 is a special case. It is not a prime number. All right, fill in the Venn diagram below with the actual numbers from the spinner. So we're going to go through each of these 8 numbers. If it's even, we're going to put it in the even circle. If it's prime, we're going to put it in the prime circle. If it's both even and prime, it's going to go in this middle section here. And if it's neither, it's going to go on the outside of those. Okay, so 1. Is 1 even? No. Is 1 prime? No, because it's that special case where 1 times 1 is 1, but it's not considered a prime number, so it's going to go on the outside. 2. Is 2 even? Yes. Is 2 prime? Yeah, the only factors of 2 are 1 times 2. So that's going to go in the middle. Now let's do 3. Is 3 even? No. Is 3 prime? Yes. So we're going to put 3 in the prime circle. 4. Is 4 even? Yes. Is it prime? No, because 2 times 2 is 4. Is 5 even? No. Is 5 prime? Yes. 6. Is 6 even? Yes. Is 6 prime? No. So 2 times 3 is 6. So that's just going to go in the even circle. 7. Is 7 even? No. Is 7 prime? Yes. So it's going to go in the primes. And 8. Is 8 even? Yes. Is 8 prime? No. So now we've gone through all of them. Okay, so we're going to use this example for this next section. But before we go to the next questions, I just want to talk about what union and intersection means for sets. So when you have 2 sets, let's say they're set A and set B, if we're talking about their union, then we're talking about everything that's in A and everything that's in B. So think about when you marry someone, you unite together and you bring all of your stuff together with all of your spouse's stuff. And that is a union of 2 people bringing all of their stuff, or like they're moving into a house and you all bring all your stuff into the same house together to move in. Union is everything in A and everything in B. An intersection is where, kind of think of it as where the 2 circles intersect with each other. The intersection is just that middle piece in there. It's where they overlap. It's the overlap part. And you can see here, union is an everything between the 2 circles, and it does not include what's outside. And the intersection is just that little piece in the middle where they overlap. Also, you need to know the symbols. So this U symbol, that stands for union. And an upside down U, that stands for intersection, which ends in an N. Maybe that might help you remember it. But that's like an and, A and B. It's the intersection of both of them. All right, so for number 4, I want you to look at number 3 again, the spinner up above, and find the union of A and B. So we're looking for A union B or A or B. Union is or. So I'm looking for what's in A. Well, in A, I'm going to go to my circle here. In the blue circle, I have 2, 4, 6, and 8. In the green circle, I have 2, 3, 5, and 7. I said 2 twice, so I don't need to write it twice. So I have 2, 3, 4, 5, 6, 7, 8. So everything except 1 would be considered in the union. Anything that was in either the blue or the green circle, or both. Intersection, A intersect B, that's going to be whatever's in that little section that I outlined in gray right here. So what is in both of them? Where do they overlap? The only one that is both even and prime is a 2. So the intersection of A and B would just be 2. Number 5, and this is going to come up in our probability. So right now we're just talking N means number. We're not talking probability. So why is the equation the number in A or B? So that's 1, 2, 3, 4, 5, 6, 7. 7 are in A or B, equal to the number in A plus the number in B, generally not true. What would be the correct modification to make it true? Use the last example to help explain. So what I'm asking is, why is 7? So the number in A is 1, 2, 3, 4, and the number in B is 1, 2, 3, 4. So we said the union has 7 terms in it. So is 4 in A plus 4 in B, well, that's equal to 8. That's not equal to 7, because N means the number in A plus the number in B. So there's 4 elements in A, 4 in B. That adds to 8, not 7, which is how many are in our union. Why is that not true? And come up with a modification to make it true. So pause the video, take a moment, see if you can figure this out. All right, so hopefully what you figured out is that the reason it's not equaling each other is because that intersection is counting twice. We counted the 2 with A, and we also counted it with B. So what you want to do to modify this, the number that's in A or B, so our union, is equal to the number in A plus the number in B, but then you need to subtract however many elements are in your intersection. However many are in that little piece of overlap. Because you're counting them twice, you only want to count them once. So if you count them in A, we counted the 2 in A, then we counted the 2 again in B, we want to subtract how many were in there. So there's 4 in A, there's 4 elements in B, there's 1 element in that intersection, so the 2 occurred twice in each of these, so we say that there's 1 element there. There's only 1 number in this intersection right here, and 4 plus 4 is 8, minus 1 is 7, and that is the correct number. And this is also going to apply when we do probabilities. So let's take a quick look at what that would mean. So if you talk about probability here, this would be like saying find the probability of getting a number in the union. Well, the probability of getting one of these numbers is 7 out of 8. There's 7 numbers. The only one we didn't include was the wasn't 1, because 1 wasn't prime and it wasn't even. What's the probability of getting an A? Well, A would be, there were 4 out of 8 terms, plus the probability of B, again, we counted 4 out of 8 terms, but these are not equal to each other because 4 plus 4 would give us 8 out of 8. So you would want to subtract the probability of getting your intersection. So we have one term there, so we would subtract 1 out of 8. And that would give you your probability of getting the union, or A or B, which is 7 out of 8. So this applies to both when you're just finding the number versus, that's why I used n here, versus when you're finding the probability. Okay, number 6. Given the two sets below, give the sets that represent their union and their intersection. So again, a good time to pause the video, see if you can write these out on your own. All right, so for union, that means anything that's an A or B. So I'm starting with a 1 over here. Then the next number I see is 3. Then they both have a 5. Then I see a 7. Then a 9 in both of them. And then an 11 in A. I see a 13 in both of them. And then I see a 17 in B. So this includes every single number. Only write it out once in A and in B. So A or B are union. Now A intersect B. So that means what numbers are in both of them. So I circled them as we went through. So 5 was in both, 9 was in both, and 13 is in both. So if I wanted the probability of the intersection, that's when you would take how many numbers you have out of your total to find probabilities. Right now, we're just finding the actual elements in each of those sets. All right, number 7. I didn't ask for the probability, so we're not going to do that right now. Number 7, Red Hook High School has 480 freshmen. Of those freshmen, 333 take algebra, 306 take bio, and 188 take both algebra and bio. Which of the following represents the number of freshmen who take at least one of these two classes? Okay, so to do this, we're comparing two things, algebra and bio. So to get an idea of what we're talking about, I'm going to draw a Venn diagram. And then we'll talk about how to do it using the equation as well. So this is going to be algebra, and the blue circle is going to be bio. I know there are 333 students that take algebra. I know there are 306 that take bio, and 188 that take both. So I'm going to put that right in the middle here. To figure out how many students take just algebra, so in the green circle, it has to total to 333. I know there's 188 already in there that are taking algebra and bio. So I'm going to do 333 minus 188, and that gives me 145 students are taking algebra but not bio. And then I'm going to do the same thing to find how many are taking bio and not algebra. I know there's a total of 306 in this whole blue circle. 188 of them are also taking algebra, so I'm left with 118 are taking bio but not taking algebra. And we want to know how many are taking at least one of these two classes. So we want to take 145 is just algebra, 188 are taking both, and 118 are taking just bio. We add those together, gives us 451 students. So something to think about, would it have worked if I just added 333 plus 306? Does that give me the same answer? And the answer is no, because you have those 188 students that are overlapped. So they're actually counted in the green circle and the blue circle. So if you wanted to use a formula, you could use an equation and say, okay, well, we're not talking about probability, we're talking about just the number of students. So I'm going to use n. So I could say the number in the union, so taking A or B, is what we're looking for, would be the number in A plus the number of students taking bio minus the number of students that are in both. because we don't want to count those 2 times. I don't know why this is flashing so much. All right, so to find this, we'd say how many are in A? 333 plus bio is 306. And then in the middle, we have 188. And you can throw that right into your calculator, and it gives you also 451. So either method here, Venn diagram or that equation, would work. All right, and number 8. Evie was doing a science fair project by surveying her bio class. She found that of the 30 students in the class, 15 had brown hair, 17 had blue eyes, and 6 had neither brown hair nor blue eyes. Determine the number of students who had brown hair and blue eyes. So let's take a look at it again a couple different ways. So first, let's just reason this out using a Venn diagram. So let's do the red circle is going to represent if you have brown hair, and the blue circle will be blue eyes. And I'm going to draw a rectangle around it to represent my sample space. And I especially want to do that because I see that it says 6 had neither brown hair nor blue eyes. So that's not going to go in either circle. So I'm going to just put this out into my box in my sample space. I know that there's a total of 30 students in the class. I'm just going to write that at the top of my box because I know that all these numbers added together inside the rectangle have to add to 30. So I know that 15 have brown hair, and I know that 17 total have blue eyes. So the red circle needs to add to a total of 15. The blue circle needs to add to a total of 17. I want to know what's in this overlap. How many have both? Okay, so think of a way, maybe pause the video here, try to think of a way how could we calculate this? All right, so maybe you're thinking, well, I know I have 30 students and 6 of them have neither. So that leaves me with 24 students that have to go between the blue circle and the red circle. Well, if I take the brown-haired students plus the blue-eyed students, and that gives me 32 students total. I'm only allowed to have 24 because that's all I have left, because I know 6 don't have either brown hair and they don't have blue eyes. So I have more than I actually have left. So what does that tell me? How many extra do I have? We'll take 32, subtract 24, and that gives me 8. So that means I have 8 extra students. So that must mean there's 8 that have both brown hair and blue eyes. That also tells us then if this adds to 15, there must be 7 that have only brown hair, and there must be 9, 17 minus 8 gives me 9 that have only blue eyes. Another way of doing it, for those of you who that didn't make sense for, you could have said, okay, well, I know I have 15 kids that have brown hair, 17 with blue eyes, and 6 that have neither. That gives me 38. Then you could say, how many extra students do I have? Because I only have 30 students in the class. I have 8 extra. So 8 students that you, in your overcount, or that overlap. So that would be in that center section. Okay, and the last way to do it, so I think those ways are probably the most common that make sense to students, but just as we get on to probability, good to see how to use the formula as well. So if I wanted to find the number of students in my union, I know that that's equal to the number in A plus the number in B minus the number in my intersection. And I'm looking for what's in my intersection. So this way is a bit more complicated. So I know in my union, so how many I have in the red and the blue circle, that's going to give me my 24. I know I have 15 in A, I have 17 in B, minus my intersection, and then I'm solving for this as if it was just an x. So I would take my 15 plus 17, which is 32, and then subtract that over to the other side, get negative 8 equals negative intersection here, divide by negative on both sides, and we get 8. So either way that you do it, you should end up with 8 students that have both. I think for most of you, probably easier to do it using that Venn diagram to figure it out. So a lot of different things going on today in this lesson, tree diagrams, probability, a little intro, sets, unions, intersections. So make sure you really feel comfortable with your vocabulary as we move forward with more probability. All right, I hope you guys are staying healthy. I miss you. Pie out.